In this video, we'll be continuing our discussion of graph transformations. In our previous video, we talked about shifts. In this one, we'll be talking about scales. We'll see that scaling a graph will mean that we are stretching or compressing our graph in some way. Just like our previous video, what we want to do is look at the function f of x equals x squared, and what we'll do is compare it with the graph of y equals 2 times f of x and y equals 1/2 times f of x. From our previous video, we saw that adding or subtracting numbers corresponded with shifts. When we do scales, we're instead multiplying by a number. So here we have a multiplication by 2, and here we have a multiplication by 1/2. First off, we have the graph of f of x equals x squared already displayed here. The table of values was what we had computed in our previous video, and we saw that when we plot the points and graph the equation, we have the following graph. So now let's look at the graph of the equation y equals 2 times f of x. With our function being the x squared function, this is the equation y equals 2 times x squared. Let's fill out our table of values. For our x values, let's look at x values from -2 all the way to 2. To find the corresponding y values, we want to plug in the x values in this equation. So when x is -2, we do 2 times -2 squared, which is 2 times 4, giving us 8. When x is -1, we do 2 times -1 squared, which is 2 times +1, giving us 2. When x is 0, we do 2 times 0 squared, which is just 2 times 0, which is still 0. Plugging in x equals 1, we have 2 times 1 squared, which is 2 times 1, giving us 2. And then lastly, when x is 2, 2 times 2 squared would be 2 times 4, which is 8. Now, when we compare this blue table of values with the original purple table of values, we see that the y-coordinates are all doubled. Originally, for the x squared function, we have 4, 1, 0, 1, 4. Now, for the equation y equals 2 times our function, it's 8, 2, 0, 2, 8. So again, all of the y-coordinates are doubled. Now let's plot our points and draw the graph. We have -2, 8, then -1, 2, 0, 0, 1, 2, and then 2, 8. Connecting these points, we get the following graph. So this here is the graph of the equation y equals 2 times x squared. We say our graph here is vertically scaled by a factor of 2, or vertically stretched by a factor of 2. I like to think about this as drawing our x squared function on a piece of slime, then stretching that piece of slime vertically so that it's twice as tall as it used to be. And again, when we compare the points in my original graph with the points on the transformed graph, all of its y-coordinates are doubled. Let's now look at the equation y equals 1/2 times f of x. With our function being the x squared function, this is y equals 1/2 times x squared. Let's first fill out a table of values for this equation. Let's pick the x values from -2 all the way to 2. To find the y-coordinates, we plug these x values into the equation y equals 1/2 x squared. So when we plug in x equals -2, we have 1/2 times -2 squared, which is 1/2 times 4, giving us 2. When we plug in x equals -1, we have 1/2 times -1 squared, so that's 1/2 times +1, which is 1/2. When we plug in x equals 0, this is 1/2 times 0 squared, which is 1/2 times 0, which is 0. Plugging in x equals 1, we have 1/2 times 1 squared. That's just 1/2 times 1, which is 1/2. Lastly, plugging in x equals 2, 1/2 times 2 squared would be 1/2 times 4, which is 2. When we compare this red table of values with the original purple table of values, we see that all of the y-coordinates are halved. Originally, for the x squared function, the y values were 4, 1, 0, 1, and 4. But now, for the 1/2 x squared equation, we have 2, 1/2, 0, 1/2, 2. So again, all of our y values were halved. Let's now plot these points and draw our graph. We have negative 2, comma 2, negative 1, comma 1/2, 0, comma 0, 1, comma 1/2, and then 2, comma 2. Connecting these points, we have the following graph. So this is the graph of the equation y equals 1/2 times x squared. This time when we compare the purple graph to our red graph, we say that our graph is vertically scaled by a factor of 1/2. Or we also say that it's vertically compressed by a factor of 1/2. Again, you can imagine drawing your x squared function on a piece of slime and then squishing that slime down vertically so that it's half the height as it used to be. When we compare the points in our original purple graph with the points on our transformed red graph, we see that all of the y coordinates are half of what they used to be. So from these examples, we've observed the following. If we have some number c times our function, what we're doing is a vertical scale by a factor of c, which means that we want to take all of our points from our original graph and multiply the y coordinates by c. Now, if our c value is greater than 1, it means we're stretching our graph vertically. And if the c value is between 0 and 1, then we're compressing our graph vertically. Next, we'll look at a different type of scaling. We're still going to be multiplying by 2 and multiplying by 1/2. This time, we're going to be multiplying those numbers to our input. Let's see what kind of effect that will have. So in this example, what we want to do is work with the x squared function like we've been doing, but then we want to compare it to the graphs of y equals f of 2 times x and y equals f of 1/2 times x. So again, the multiplication by 2 and the multiplication by 1/2 is done in the input. And since these operations are done to the input, we should expect that this will affect our x values. First, let's look at y equals f of 2 times x. If we want to evaluate f of 2 times x, we take x in our original equation and we replace it with our new input 2 times x. So the equation is going to be y equals, in parentheses, 2 times x squared. Again, since we replaced our input x with the new input 2 times x, we expect that this transformation affects our x values. So if we want to compare this with the original graph, when we make our table of values, let's keep the y values the same. Let's do 4, 1, 0, 1, and 4 for the y values, and we'll try to figure out what x values are needed to get those y values. First, let's try to think what x value can I plug in so that we get 0 as the y value? Meaning, what can I plug in for x here so that when I multiply by 2, then square the result, we end up with 0? Well, that's going to be x equals 0 because 0 times 2 would be 0, and then when we square it, it'll still be 0. So when I plug in x equals 0, we get y equals 0. Next, let's think about what x values we can plug in so that we get 1 as the y value. So I want to think, what number can I plug into x so that when I multiply it by 2 and then square the result, we end up with 1? Well, there are two choices. One of them would be x equals negative 1/2, because if we do negative 1/2 times 2, that's going to be negative 1. So when we square the result, this gives us positive 1. So when x is negative 1/2, the corresponding y value is positive 1. Another choice would be x equals positive 1/2, because if we plug in positive 1/2, then multiply by 2, this gives us 1. Then if we square the result, it's still going to be 1. So when x is 1/2, the corresponding y value is 1. Now let's think about how we would get 4 as the y value. So what can we plug in for x so that when I multiply by 2 and square the result, we get 4? Again, there's going to be two choices. we can have x equals -1, because if we plug in -1 here, multiply that by 2, we get -2, then square the result, we get +4. So when x is -1, the corresponding y value is +4. Another option for x would be x equals +1, because if we take 1 and multiply by 2, that's going to give us 2, then square the result, we're going to get 4. So when x is equal to 1, the corresponding y value is 4. So let's now compare our blue table of values with our original purple table of values. You might notice that all of the x coordinates were halved. Originally, the x values were -2, -1, 0, 1, and 2. But with our transformation, the x values are now -1, -1/2, 0, 1/2, and 1. So again, this multiplication by 2 in the input led to the x coordinates being halved. If we plot these points, we have -1, 4, -1/2, 1, 0, 0, 1/2, 1, and then 1, 4. Connecting these points, we get the following graph. So this here is the graph of y equals, in parentheses, 2x squared. So comparing the original purple graph with our new blue graph, we would say that our graph was horizontally scaled by a factor of 1/2. Or we would say that our graph was horizontally compressed by a factor of 1/2. Again, you can picture this as drawing your original x squared function on a piece of slime, but this time we're squishing our piece of slime in so that it's half as wide as it used to be. And essentially, if you compare the points on your original graph with the points on your transformed graph, all of the x coordinates are multiplied by 1/2. One important thing to note here is the reciprocal effect of the transformation. We replaced the original x in our input with 2 times x. But instead of multiplying all the x values by 2, they were actually multiplied by the reciprocal, 1/2. Let's now take a look at the equation y equals f of 1/2 times x. To evaluate f of 1/2 times x, we take x in our original function and replace it with our new input 1/2 x. So our equation is going to look like y equals, in parentheses, 1/2 times x squared. Again, when we make our table of values, we expect this transformation to affect our x values. So in order to make a comparison with our original purple table, we'll keep the y values the same. We'll keep them as 4, 1, 0, 1, and 4. So let's now think about what x values we need so that we get these y values. Let's start by figuring out the x coordinate needed to get the y value 0. So what can we plug in for x so that when I multiply it by 1/2 and square the result, we get 0? Well, that's going to be x equals 0, because 0 times 1/2 is 0, and then when I square it, we get 0. So when we plug in x equals 0, the corresponding y value is 0. Next, let's think about what x values I can plug in so that we get 1 as the corresponding y value. So we need to come up with x values such that when I multiply it by 1/2, then square the result, we get 1 as the corresponding y value. One option would be x equals -2, because -2 times 1/2 gives me -1, so when I square it, it becomes +1. So when x is -2, the corresponding y value is +1. Another option would be x equals +2, because 2 times 1/2 would give us 1, so when I square it, it's still 1. So when x is equal to 2, the corresponding y value is 1. Next, let's think about what x values I can plug in so that we get 4 as the corresponding y value. So whatever x we plug in, we need to multiply it by 1/2, then square the result. One option would be x equals -4, because -4 times 1/2 gives us -2, so when I square it, it becomes +4. So when x is -4, the corresponding y value is +4. Another option would be x equals +4, because 4 times 1/2 gives us 2, and then 2 squared gives us 4. So when x is 4, the corresponding y value is also 4. Let's now compare this red table of values with the original purple table of values. You might notice that all of the x-coordinates are doubled. Originally, for the x-squared function, the x values were -2, -1, 0, 1, and 2. But now, for the transformed equation, y equals in parentheses 1/2 x squared, the x values are -4, -2, 0, 2, and 4. So when we replace the original input x with 1/2 times x, all of our x values were multiplied by 2. Let's now plot our points and draw our graph. We have the point -4, 4, -2, 1, 0, 0, 2, 1, and 4, 4. Connecting our points here, we get the following graph. So this is the graph of the equation y equals in parentheses 1/2 times x squared. When we compare our original purple graph with this red transformed graph, we say that it is horizontally scaled by a factor of 2. Or we say that our graph is horizontally stretched by a factor of 2. Again, to obtain this graph, you can imagine drawing your original purple graph on a piece of slime and then stretching that piece of slime horizontally so that it's twice as wide as it used to be. And when we compare the points in the original purple graph with the points on the red graph, all of the x-coordinates are doubled. So again, there's this reciprocal effect. When we replace the original input x with the new input 1/2 times x, instead of taking the x-coordinates and multiplying them by 1/2, they're actually multiplied by the reciprocal. They're multiplied by 2. So from our examples here, we've observed the following. When we replace the original input x with c times x, this leads to a horizontal scale by a factor of the reciprocal 1/c. And what this means in terms of our graph is that you take all of the points in your original graph and you multiply all of the x-coordinates by 1/c. Because of this reciprocal effect, when c is greater than 1, what we have is a horizontal compression. And when c is a number between 0 and 1, we have a horizontal stretch. So in this video, we learned that when we multiply by a number, we're scaling our graph in some way. And scaling just means that we're stretching or compressing our graph. In this video, you might notice that the numbers that we multiplied were all positive numbers. What happens if we multiply by a negative number? That's what we'll explore in our next video.